All right, in this video, I'm going to be showing the relationship that exists between areal or superficial expansivity, which is denoted by beta, and the coefficient of linear expansion, also known as the linear expansivity. So in the previous video, I was able to show the relationship that exists between the cubic or volume expansivity and the linear expansivity. So we are going to follow the same procedure. So recall, let's start. Recall that linear expansivity alpha is given to be what? L2 minus L1 over L1 times theta. Don't forget that this theta is the same thing as delta theta is got to what? Theta. So for the purpose of the proof, that is why I decided to use theta to make it easier. Then we also have that the area or superficial expansivity beta is given to be what? A2 minus A1 over A1 times theta. So in this case, we'll call this equation 1 and we'll call this equation 2. So we start from equation 1. So from equation 1, what I want to do in equation 1 is I want to make either of L2 or L1 the subject formula. So basically what I'm going to do is I will cross multiply. So from equation 1, we can have that L2 minus L1 is equal to what? Alpha L1 theta. So let's call this equation what? Equation 3. Okay. So then we can say that what? L2, I think I've always made L2 the subject formula, is equal to what? Alpha L1 theta then plus L1. I call this equation 4. Don't be carried away by the number of equations. It's just for reference purpose. So now we know that the area of a material, basically area of a square material, is given by what? A, which is equal to length times breadth. We can also express it in terms of length. That is what? L square. That's length times length. So that implies that we can see that A1 is equal to what? L1 square. And we can see that what? A2 basically is what? L2 what? L2 square. So what we have here is L2. So we can take the square and express it in terms of area. So you now say square equation what? Equation 4. Meaning that I'm taking the square of equation 4. So if I take the square of equation 4, I'm going to be having what? L2 square will give me what? Alpha L1 theta plus L1, then everything what? Square. So if I square this will return alpha L1 theta plus L1 into bracket alpha L1 theta plus L1. So if I continue this, then let's open this bracket. So if I open this bracket, I'm going to be having what? L2 square will now give us alpha L1 theta times alpha L1 theta. That will give us what? Alpha square L1 square then theta square. Then alpha L1 theta times L1, that will give us alpha L1 square theta plus alpha L1 square, alpha L1 square theta, then plus L1 times alpha L1 theta. That will give us what? Alpha L1 square theta. Then L1 times L1, that is plus what? L1, square. So if you look at this, I can actually add these two terms together. So I can have what? L2 square will now give us alpha square L1, pardon me, let me write L1 square theta square, right? Then plus 2 alpha L1 square theta square. That's plus 2 alpha L1 square theta square. Did I say theta square? Excuse me. That's 2 alpha. That's alpha L1 theta plus alpha L1. That's 2 alpha L1 square theta, then plus L1 square. So with respect to what we did in the previous video, we know that linear expansivity is a very small value. So for example, the linear expansivity for iron, like I said, is 0 in the previous video. That's 0.000012 per Kelvin. So therefore, then alpha square, in that case, that's hence alpha square and what, and alpha cube will be very small, and they will tend to what, to 0. So that implies that wherever we see alpha square, and of course we don't have alpha cube here, we take it to be equal to 0. So where do we have alpha square? So we have it here. This is the only place we have it, alpha square. So the whole of this term will be equal to what, 0. So what does that suggest? That actually suggests that we can say L2 square will now be equal to what, 2 alpha L1 square theta, then plus what, L1 square. So that is that about that, because the whole of this term has been equated to 0 due to the fact that linear expansivity is very small value. So but I established earlier on that what, A1 is equal to what, L1 square, and also A2 is equal to what, L2 square. So that implies that wherever I say L1 square and L2 square, I can replace with it A1 and A2. So I can say L2 square, that will give us what, A2 will now be what, 2 alpha, this L1 square will now be 2 alpha what, A1 plus what, plus A1. Right, so we have what, A2 is equal to 2 alpha A1. I didn't put theta here, pardon me for that mistake. Yeah, 2 alpha A1, that's 2 alpha A1 theta, right, then plus A1. All right, so I can write this like I can write it in form of, I can bring A1 to this side such that I have A2 minus A1 will give us what, 2 alpha what, A1 what, theta. All right, so I can call this, I don't know if I've named any equation yet. Did I name any equation? Okay, 4. So I can call this equation 5. So let's call this equation 5. But you need to recall that what, beta in this case is A2 minus A1 over what, A1 times what, theta. So if I cross multiply, I can say A2 minus A1 is equal to what, beta what, A1 theta. And so let me call this equation 2 star, because an extension of equation 2. So with this understanding, we can equate equation 5 and equation 2 star, because both of them have A2 minus A1, right? So I can say, so this implies that wherever I have A2 minus A1, both of them have it, so I can equate these two. So I can turn it to beta A1 theta will now be what, 2 what, alpha A1 theta. Okay, so theta cancel theta, A1 cancel A1. So therefore beta is equal to what, 2 what, alpha. So basically what this tells us is that the area of superficial expansivity is the product of 2 and linear expansivity. So we can make linear expansivity also the subject formula. Consider alpha is equal to what, beta over 2, just like I did under cubic expansivity. I want to believe that this video has helped someone. Endeavor to subscribe and share with your friends. So see you in the next video. Thank you.